And here we go again. We are back to AP Calculus BC, working through our series convergence tests. Today's day 28. It is the direct comparison test, and full disclosure, this is my least favorite test. It seems obnoxiously tedious, and in fact, pretty much everything we learned today can be done much faster with the limit comparison test that we'll learn next class. However, there still are certain situations where this is useful, and it is definitely still tested. There might be a question like, which of these would work for a direct comparison test? So there are ways to ask it, so you can only use this. So we do need to get through this, but I think at least you'll get some interesting information about fractions as we go through, so let's begin. There's an opener, and we have a decreasing function f of x, and we're also going to know that a function g of x is smaller or less than f of x for all large values of x. So then go ahead and sketch first a potential graph that includes both f of x and g of x on the same graph, on the same coordinate plane, and then a second one where we assume that g of x is always positive. Okay. And I will show you what I mean once you try it and unpause. All right, well, one graph for our first one is, let's go ahead and just, I don't know, play around with f of x. We'll do f of x in red, and f of x is just going to do whatever the heck it wants. It just messes around, does something like that, and we'll call it f of x. Cool. Well, we know that g of x, and we'll do this one in green, has to be less than f of x. Now, when we're talking about these are outputs. So when I say less than, really I mean below. We're going to have g of x, and if we compare like a set of points right here, if here's a point, that's the y value of f of x, g of x has to be somewhere underneath that, right? And it could do something like this and could kind of, this is below everywhere. It could even mirror the graph. It could actually even touch the graph and then drop down too because of that equal sign. But either way, this is maybe a sample idea of f of x versus g of x, and just showing that, g of x is less than all the way through. Now, what about if g of x is positive? Well, I think what that's going to mean is it's going to keep f of x positive as well, right? So maybe I'll start with g of x this time. We know g of x has to be positive, so I'm only really caring about my first and maybe second quadrant here. So if g of x is positive, it can never dip below the x-axis. Maybe it goes up here. Maybe there's like an asymptote or something like that. Cool. And for f of x to always be above that, f of x can never be down here. It can never go negative. It's really stuck up in the positive side. Maybe it does its own thing over here. We get the idea. Now, these two graphs are pretty important for the direct comparison test, and that is our first blank down below, because what we're going to do is we're going to compare two series, or rather two sequences, against each other. And if certain criteria are met, then we're going to be able to decide if the series based on those sequences converge or diverge. So let's go ahead and compare really four scenarios, whatever we're going to say, down below. And they're going to deal with the series of a sub k and the series of b sub k. We are given that the sequence a sub k is smaller term by term than the sequence b sub k. So what that might be, and you don't need to write this part because we'll see some examples in a bit, maybe a sub k, that's supposed to be the smaller one, is like 1, 2, 3, so on and so forth. And then term for term, b sub k, which is supposed to be the bigger one, let's just make it 2, 3, 4. All right, looking at those two patterns, is it fairly apparent that b, the one in red, is larger than a? That's all this is telling us right here. And then it also says 0 is less than a sub k, which means that, of course, our series have to have our sequences have to have positive terms. But then they also tell us one other important thing. They tell us that the sum of b sub k, the series for b sub k, converges. And because we know that, because we know it converges, by the nth term test for divergence, we know that the limit as n approaches infinity of the sequence, not the series, of the sequence, has to equal 0, right? That's our nth term test right there. And so then something interesting happens. If I wanted to go through and graph this sequence b sub k, if the limit of the individual terms are getting closer to 0, well, it certainly can't look like this guy up above. Those terms are getting bigger, 4, then 5, then 6. Our terms have to be getting closer to 0. So maybe I'll show it something like this. There's first term, discrete because they're individual terms, and maybe we have some sort of asymptote down here, right? But they're eventually approaching 0. But what else do we know? We also know that a sub k has to be strictly less than or possibly equal to b sub k. So maybe it starts off like equal, and then eventually it's like dropping below it. If it's below, it's really going to get squeezed, kind of like the squeeze theorem, the sandwich theorem. It's really going to get squeezed in between the red function and 0, because it will also have to go to 0. If eventually this is 0, then in order for a sub k to stay below b sub k, it has to go to 0 as well. So right away, because of this, we know that the limit as n approaches infinity, oh, I guess I should be using k here. Sorry, I'm using n and k interchangeably, and that's really silly of me. I'm going to stick with, well, it looks like I just go back and forth here, so that's dumb. I guess I'll stick with k, though, since that's what your book uses. So a sub k also has to equal 0, which means a sub k may converge. However, the fact that a larger sequence, if you sum up the larger sequence and that converges, then what does that tell you about a sub k, the smaller sequence? Yep, you guessed it. The conclusion of this is that from k equals 1 to infinity of a sub k, the series for a sub a also converges. And honestly, I have to picture a graph for this every single time. I have to go through and draw this relationship to understand what's happening, because there's 4 possibilities, and we're going to go through all 4 of them. But either way, we knew that b sub k converged. I did that in red, so a sub k had to converge, and because the sum of b sub k of larger numbers equals a value, then the sum of smaller numbers will certainly not equal infinity. It can't be bigger, so it also has to converge. So let's look at another one. All right, given this same situation where we have a sub k and b sub k greater than 0, a sub k less than b sub k, and we know b sub k diverges. Well, what does divergence mean? Divergence could mean that my series still gets closer to 0. Think of the sequence 1 over n, right? 1 over n gets close to 0 and diverges. But we could also maybe even think of like n to the 1/2, right? Gets closer to 0 too, something like that. But then the question is, what do we know about b sub k? Well, b sub k is certainly still below a sub k, which means that these are smaller numbers, and if you add up smaller numbers, they could still converge. But what if we had n to the 1/2 power, and then we got a little bigger than that, so the fraction became smaller, and I said that this one is n to the 5/6. 5/6 is bigger than 1/2, and when the bottom of a fraction is bigger, it makes a smaller number. So though these are 2 possible sequences here. Okay, does n to the 5/6 converge when you do a sum? Well, no, because it's a p series with p still less than or equal to 1. Or in fact, what really could happen here is b sub k could be diverging, because b sub k could be going off to infinity, and if you add infinitely large numbers together, then you're certainly going to get divergence, and a sub k could follow right after that, or a sub k could get small really fast and could converge. So this relationship here, knowing that b sub k diverges, actually tells us nothing about a sub k. So in this case, we would say we can't determine the convergence of the summation from k equals 1 to infinity of a sub k. So in one way we can, but with a different situation we can't. And that's going to happen the same way down below. So let's take a peek at these two. Given, and now notice they switched the order here. We're still talking about the convergence of b sub k, but they switched the order. Now b sub k is smaller. Okay, so they're saying, given that b sub k converges, or the series of b sub k converges, which of course again means the limit as k approaches infinity of b sub k equals 0, so we could probably graph that. It's got to go down to 0 eventually, and then if you add up every single one of these y values over here, you get a concrete answer. And a sub k is above that. Well, if a sub k is above that, do we know that if we add up these guys, we also get a number? No, we don't. In fact, we don't even know it follows f of x like that. What if it went down and then kind of curled back up forever? Well, if you added up all those terms, that could be divergent. Or it could be exactly the same as b sub k, and it could be convergent. So this is another situation where we can't determine the convergence of the sum from k equals 1 to infinity of a sub k. So two situations where we can't know, or we don't know for sure. But then let's look at this last one. All right, at least there is some symmetry in this. Again, similar setup to the one that we just did. So again, I'll sketch a nice little graph over here. And now we know that b sub k is smaller than a sub k, and b sub k diverges. So I'll give you a pretty obvious graph first. If it diverges, then what if my graph looked something like this? Right? Diverges because we're adding up values that are larger and larger every time. And if a sub k is above this, well then a sub k has to have even larger values that we're adding up. So clearly a sub k is also going to diverge. And it's a little bit trickier to see if I had drawn it the other way, but it would still work, right? So if I did something like this and I said, okay, we know that b sub k diverges, right? Even though it's going to 0, maybe b sub k is like 1 over n or something. If you're adding up each of these, it diverges. And a sub k is above that. Well, now again, you're adding, think about visually, the green function is above the red one, so larger values. You're adding up larger values here. And if you're adding up larger values, then of course that's going to diverge as well. So what can we do here? We know then that from k equals 1 to infinity of a sub k converges. This altogether is known as the direct comparison test. Now, of course, I haven't actually shown you how to use this yet, but we really do need the conclusion of these two boxes that I'm outlining right here, where one situation will show us that a function converges and the other one will show us that a function diverges. Oh, and I'm sorry, I wrote converges here. Oh my gosh, worst day ever. This should be diverges. I just said diverges like 50 times. That should be diverges. So there's one scenario where we can figure out that a sub k converges, another one where it diverges, and then there's two scenarios where the direct comparison test doesn't help us. And that's why this can be frustrating. You can be like, oh yes, I found the perfect series to compare this to, and then it turns out to not help you. And you're like, no. But let's get to it. So the trickiest part about the direct comparison test is that you actually need to choose a function, or maybe a sequence is a better term for that, where you not only know its convergence or divergence, so you need to pick something like 1 over n or 1 over n squared, where you're like, I know that's a p-series, that converges sort of thing. But you also need to know that it's bounded by the other function, or it bounds the other function. Now, bounding we've referenced a couple times, and we'll dive really head deep into it later on this unit and next unit. But it's really the idea that although an asymptote can bound a function, it doesn't have to be an asymptote. For example, you can picture the graph of the sine of x, and I'll just quickly remind you of the graph of sine of x looks something like this, right? Sine of x is bounded above by x equals 1, because it never rises above that, but it's also bounded below by x equals negative 1. However, there's no asymptote here, right? It doesn't approach anything at infinity. It's just bounded. It's squished between. It can't escape the values of 1 and negative 1. Now, the technical definition for a bound is that a sequence or a function is bounded by some number m. They usually use m for, I think maximum is pretty commonly understood why they use m here, such that the absolute value of every term is less than or equal to m for all relevant values. So bounding, it might not be bounded like right here, but eventually a function is going to reach a pattern if it's going to be bounded as we move to infinity. Now, why is that important? Well, let's take a look. We're going to use the direct comparison test to identify the convergence of this series. Okay, now again, the tricky part first. We're going to choose a series that behaves very, very similar to this one, but for which we actually know the convergence or divergence. Well, to me, if we're talking about infinity, then I'm thinking dominance. I'm thinking probably the series of 1 divided by the square root of n. Or if we rewrote this, right, from n equals 4 to infinity. This would be 1 over n to the 1/2. Why am I picking this series? I'm picking the series because this is a p series. It's a p series with p less than 1, so this is a divergent series. Now, we also need to make sure that this divergent series and this series over here, or rather the sequences, are comparable. And they need to be comparable by looking at each individual term and making sure there's a consistent pattern that you can actually figure out with each term. So let's take a look at each of the sequences. And I'll try to stack them on top of each other. I know there's not a lot of room here. You might have to write kind of small, but we'll see what we can do. So 1 over n minus 3. My first term comes from when n is 4. That becomes 1 over the square root of 1. And yes, I know you can reduce that. I'm not going to, though, but you can. The reason I'm not going to reduce it is going to be made very clear in just a second. When we plug in 5, we get 1 over the square root of 2, and you can't reduce that. And if you're comparing patterns, it's usually pretty silly to reduce one fraction but not reduce another. We either want to reduce all of them or none of them. That way you can see the pattern a little bit more clearly. And I think the pattern here becomes fairly obvious at this point. It looks something like this. Okay? And then let's take our comparison series, 1 over the square root of n. We're starting at 4, so it becomes 1 over the square root of 4, 1 over the square root of 5, and so on and so forth. I think we can see this same pattern. But then, and this is the tricky part, and we have to be good with fractions, and we'll work on this, we need to be able to decide which fraction is larger versus smaller. I think you'd probably be comfortable saying that the yellow sequence has larger denominators. And so one thing we're really going to have to keep straight is that if you have a fraction with a larger denominator, it becomes a smaller number. And the reason why, we'll take 1 over just a nice number like 10. Imagine you take $1, you split it among 10 people. How much does each person get? Well, 10 cents. But now take that same dollar and spread it over 100 people, larger denominator. How much does each person get? Well, now only 1 penny. So by increasing the denominator, we make the actual value of the fraction smaller. So these larger denominators mean that those fractions are smaller than the ones up above, which means we can take this series 1 over the square root of n, and we can say that that is definitely less than, and we don't even need the equal, they're not going to be equal in this case, but you could put it if you'd like, definitely less than 1 over the square root of n minus 3. All right, well then, does that help us? And that's the second question that also makes this a little bit tricky. So again, I mentioned I always have to draw a quick little graph here. And although I know it's not quite the case, I usually cheat a little bit on these graphs. And I say, okay, let's talk about the convergence of this series, or divergence. Well, for this series, we know that p is definitely less than 1, which means it's divergent. And actually, we're going to need to explain that later on, so we should probably do it right now, right? So we should say, the sum from n equals 4 to infinity of 1 over n to the 1/2 is divergent. And we'll say by the p-series test because, no comma needed there, because p equals 1/2, which is less than or equal to 1. Great. We've explained why that's divergent. Now, technically, this sequence, if you graph it, goes to 0. But and again, this isn't, College Board approved or anything, but I always think about graphing something that's divergent. I always send that thing to infinity. And again, you don't have to, but it just helps me to analyze. So now let's go ahead and think about this relationship over here. This tells us that 1 over n, the sequence, is smaller than 1 over n minus 3, square root of n minus 3, which means if you put comparable points on here, 1 over n minus 3 also gets pushed up to infinity. And again, technically this isn't the case, but I think it's, again, easy to visualize. And so if we sum up all of the yellow terms and we get something that's infinitely large divergent, then if you sum up larger terms than that, then it's certainly still going to be divergent. Right? So what do we do here? Well, then we're going to bring in the original series and quote the direct comparison test. Right? So you can talk about the sequences. That's what I like to do. So then I would say something like, as 1 over the square root of n is less than 1 over the square root of n minus 3, then we always state the name of the test, the direct comparison test proves the sum from n equals 4 to infinity of 1 over the square root of n minus 3 diverges. So, a bit of work for sure. Comparing fractions is obnoxious. And then I would honestly suggest you don't memorize this. You can if you want. I literally draw a picture every time. It really helps me. And if something's divergent, I send it going up. If something's convergent, I send it going down. Now, again, that is not the actual graph. That's just the way that I like to remember it. So, totally up to you. You'll notice what we did when we picked a series to compare is I talked about dominance. I pretty much said, let's just compare it to something we know, and usually that has to do with just knocking off a coefficient or taking out something that's adding or subtracting. So let's go ahead and try one more. Okay. Use the comparison test to determine whether the following series will converge. Well, looking at this guy, 1 over 3 to the n plus n, I'm going to probably compare 1 over 3 to the n plus n with the series 1 over 3 to the n. I mean, that makes a decent amount of sense to me. They're pretty darn similar. In terms of dominance at infinity, this plus n isn't doing much. It's controlled by that 3 to the n, so let's take a peek. 1 over 3 to the n, we're starting at 1 here, will give me 1/3, 1/9, 1/27th, we'll do one more, 1/81st. The original sequence will give me 1 over 3 to the n plus n, which is, and this one's going to take me a little bit longer, I think, but really we could just take all of these and add 1, 2, 3, and 4 to it, right? So if we add 1, we get 1/4. If we add 2, we get 1/11th. 3 is 1/30th, and 4 is 1/85th. And then we need to compare these terms. Think in terms of the denominator, no pun intended. These denominators are larger, which means overall the fraction is smaller. So I think we would probably be correct in saying that 1 over 3 to the n plus n as a sequence is strictly less than 1 divided by 3 to the n. So we have a relationship. Now, the next thing we need to do, and you really should have done this in the beginning, is if we pick a comparison series, we better make sure we know if that converges or diverges. 1 over 3 to the n might be a little bit weird until you realize that 1 over 3 to the n is actually 1/3 to the n. And that's a geometric series. And that geometric series converges because r is less than 1. So let's at least put that part in words, and then we can go back and see if we actually learned anything out of this. So, we'll do the summation. As the sum from n equals 1 to infinity of 1/3 to the n is geometric with r equal to 1/3, which is definitely less than 1, then, and I'm really trying to avoid it. I wanted to say it right here converges, but I'm going to be better than that. Then the sum from 1/3 to the n converges. All right, well, now does that mean we know convergence for the other one? I'm going to again sketch a little graph. So here's my little graph down here. We know that 1/3 to the n converges. Okay, so that means, and again, I'll send it to the x-axis if it converges every time. That means we summed up all these individual points and they actually summed to a specific value. Now they're saying we know that this original sequence is actually smaller than that. So that means that the y values are below or possibly equal to it. So if you summed large values and they equaled a number, if you sum smaller ones, they are certainly still going to equal a number. The number is going to be smaller or equal to what we got for the red one. So this convergence test will tell us, or this direct comparison test will tell us that our original series converges. So let's put that into words, right? So we'd say something like, as 1 over 3 to the n plus n is less than, oops, that's not great. There we go, 1 divided by 3 to the n, then the direct comparison test proves that the sum from 1 to infinity of 1 divided by 3 to the n plus n converges. And I should tell you too, I really should be putting one more thing in here. I should be stating that both of these series are positive, because if they weren't both positive, then it would be possible for this guy to go down forever, and then you'd be adding super big negative numbers. So you probably should work positive numbers in here somewhere. Now, we've talked a little bit about fractions here, but you should, or maybe you noticed, maybe you haven't, that you can actually determine if the comparison series is larger or smaller without writing out these terms right here, just by knowing a couple facts about fractions. Right, so let's go ahead and look at two comparison fractions here. I'm going to look at the fraction a divided by b plus c, and I'm going to compare it to a divided by b. Well, what's happening? Well, originally this was the denominator. By taking away the plus c, the denominator becomes smaller. And what happens if a denominator becomes smaller? Let's take a look. Let's compare. Let's pretend it started at like 1/100th, and we stripped away something, and now it's 1/10th. Originally, each person got 1 cent if we're splitting that dollar. Now they get 10 cents. And I think that means then overall our fraction actually becomes larger. So what we could say for these here is we could say that this fraction, a divided by b, is larger than a divided by b plus c. So why don't, knowing that, you try the other three boxes here, and then we'll see how you did, and then try a couple more examples. Okay, well, let's look at our next one. We had b minus c. That's going to make the denominator smaller. And when you have a smaller denominator, the value of the fraction, oops, and I think I might have done this backwards. Oh, that's what I was doing, sorry. Okay, so this became smaller, which becomes larger. Okay, second try. If this becomes bigger, so we're taking out the minus c. So originally it was like 1 divided by 10 minus 4, so that's 1/6. Now we're taking out the minus 4 and it becomes 1/10. So if we compare 1/6 divided by 1/10, 1/10 has a larger denominator, which means it's a smaller fraction. So the denominator became larger, the value becomes smaller. So when you mess with the denominator, it has that kind of opposite effect that you would expect. Denominator bigger, value smaller. Now, the nice part, or maybe the confusing part, is if you do that with the numerator, it's really the opposite. So if you take away the plus c, then instead of it becoming a plus c, now it's just a, the numerator has become smaller. That means you have fewer things to split, which means everybody gets less. So the overall value of the fraction is smaller. And of course, the opposite is true as well. If a minus c made the denominator small, taking away the minus c numerator, makes the numerator larger. And therefore, my new fraction is going to be larger because now we have more things to split, so everybody gets a little bit more. Now, if you don't want to remember this, you can just list out the two sequences and compare them. Usually. However, what if you get something like this? This is the sum from infinity, or n equals 1 to infinity, and this looks scary. Now, I almost certainly want to get rid of this cosine squared, because then if we're comparing this, we have the sequence n divided by n squared, which is 1 over n. That's the harmonic series when we sum everything up, and we know that diverges. So keep that in mind right there. But if we're taking away cosine, we need to probably know a few things about cosine. First, we're squaring this, which means our cosine value is positive. Something squared is always positive. And we also need to remember that the largest value of regular cosine is 1. So when we square it, the largest is also 1, which means when you're doing n squared minus something, right, n squared minus something, and you take away that thing, now we're no longer subtracting up to 1, which is going to make the denominator larger. So this denominator is small. And when we compare it to n over n squared, this denominator is going to be larger. What happens when the denominator gets larger? Well, that makes the overall fraction smaller, right? They're opposites in this case. So we know that is going to be true for our sequences, though I'm going to write this over here just so I can keep track. We know that n divided by n squared minus cosine squared n is going to be greater than n over n squared. Cool. because we know this relationship, then we don't actually have to list out the fractions and we can be a little bit more efficient here. The next thing I always do again is graph it. I want to see what the heck is going on, and then if something actually works, we can write our conclusion. So what do we know about 1 over n? Well, 1 over n diverges, harmonic series. So for 1 over n, and I'll do this one in purple, I'm going to send it up to infinity because it diverges again. I know that's not quite right, but either way, that's fine. And then we know that the original sequence is larger than 1 over n, which means it's up above. And if you had a divergent series and another one that's larger than that, that one is also divergent. So now we can conclude with our direct comparison test. So we'll do something like this. As 0 is less than, what's my next largest? N over n squared, which is less than, I'm trying to get the 0 in there this time, n divided by n squared minus cosine squared of n, right? Something like that. And the sum from n equals 1 to infinity of n over n squared, which equals the sum from n equals 1 to infinity of 1 over n, is the harmonic series which diverges. Whew, this is going to be a heck of a run-on sentence, but we'll survive. Then the direct comparison test proves, I'll just do it down below, the sum from n equals 1 to infinity of n over n squared minus cosine squared of n diverges. Easy enough. Okay, we have 2 more to do, I think. Let's double check to make sure I'm not lying. Yeah, 2 more of these to do, and you'll notice these 2 are very, very similar. One of them has a +2 in the numerator, one has +2 in the denominator. So let's see if that changes anything at all. Now, again, you can always, just logically, you can think, if there's no 2 there, this reduces to 1 over n squared. That's a p-series, that's going to converge. If there's no 2 there, that's going to converge. And you're right, both of these sequences converge. But the question is, can you show that with the direct comparison test? And that's not justification on an actual AP exam either. You can't cross it out and say, convergent. You need to state a test. And so let's say you decided to try the direct comparison test. You would certainly be accurate in saying, we're going to compare it to n squared over n to the 4th. Okay, so we're going to compare n squared plus 2 over n to the 4th, and we're going to compare that to n squared over n to the 4th. Now, think about what changed here. This numerator is larger than the one on the right. A larger numerator means a larger fraction, therefore the fraction on the left is larger than the one on the right. No need to write these out. We have one sequence here, and we have a second sequence over here. Let's see if that tells us anything. Again, I always graph. We know that this guy is 1 over n squared p-series. We know that one converges. So we know that the smaller one over there, I think, definitely converges, right? That sounds pretty good to you? So then, what about the other one? Well, the other one is greater than that. And if it's greater, it's not bounded by the smaller sequence. What if the other one, the one that I have bounded in green, or in braces in green up there, what if the other one goes off to infinity? And so I think the direct comparison test here isn't actually going to tell us anything. Now, you have a couple other options. You could be really stubborn and say, okay, I'm going to find something else that does bound this, that's bigger than that, and I can actually, show a comparison sort of thing. And that would be totally fine. You're totally allowed to do that. However, don't forget that we do have other tools at our disposal. In particular, we could just split this guy up. We could say n squared over n to the 4th, right, plus same denominator, 2 over n to the 4th. And then we could simplify, and this is 1 over n squared, and this one I'll factor out the 2, n equals 1 to infinity, 1 over n to the 4th. Do those converge? Well, they do, right? Both of these series are p-series with, p greater than 1, So therefore, they converge. And we're allowed to split this up into two series here because these two series are convergent. That's the same reason we're allowed to factor out the two. This is a property of our convergent series. We can split it. However, if these didn't converge, if one of them had an issue, then we wouldn't have been allowed to split it and we'd have to look back there. But yeah, I think for me, if I wanted to prove convergence of this one, the direct comparison test would not be the right way to go. It'd be much quicker to do it this way. In fact, pretty much any test besides the direct comparison would probably be faster here, just because what seemed apparent didn't actually help us. You can do it with the direct comparison test, maybe combined with the ratio test, but why when you don't have to? Let's look at our last one. This last one, you're like, oh, is the same exact thing going to happen? Well, let's find out. We are going to compare n squared over n to the fourth plus 2, and we'll compare that to that same n squared over n to the fourth. Well, what changes here? Here we have a larger denominator, and here we have a smaller denominator. And remember, a larger denominator makes the overall fraction smaller. And look at this. That actually changes the direction of the sign. And I think that change is going to be enough to probably tell us something. Let's take a quick peek at my cheating graph over here that, again, is not very accurate. It's not going to be used for justification, but make it and then scratch it out on the AP exam if you'd like. There's nothing wrong with that. And honestly, I've never seen the direct comparison test really show up on a free response, maybe one time in 20-some years. So don't stress it too much. We know this is convergent. Boop, 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 boop. And we know that this fraction is smaller than my convergent one. Yeehaw, that's exactly what I want. If it's smaller, then it has to converge as well. So it's pretty fascinating then, these two series that are so similar. And I mean, the plus 2 makes really no difference at infinity. But this one is way easier to use the direct comparison test with. So we should probably finish our conclusion, right? As 0 is less than, that was the worst curly brace of the day, n squared divided by n to the fourth plus 2, right, which is, of course, less than n squared over n to the fourth, and the sum from n equals 1 to infinity over n squared divided by n to the fourth equals the sum from 1 to infinity of 1 over n squared, is a P series with P equal to 2, thus convergent. Then the direct comparison test proves, what does it prove? Oh, it proves that from 1 to infinity of n squared divided by n to the fourth plus 2 converges. Nothing to it. You have 2 bookwork problems to do today. I didn't want to overload you on this, mostly because I hate the direct comparison test, but also because I didn't find many problems in your book that I liked, and yeah, we should just be done with this. So you have 2 bookwork problems to try. One of them will converge, one of them will diverge. There's none of them, I think, that I gave you where it's going to be inconclusive, right? This would be an example of something that's inconclusive through the direct comparison test. And yeah, that's about it for today. So thank you for tuning in, and best of luck on the direct comparison test. No worries, because next class gets much easier. We get the limit comparison test, which is way more efficient. Good luck.